Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of finding the closest value in a binary search tree, which I'm going to be referring to as a BST from here on out. Now, I want to preface this video by saying that if you're unfamiliar with BSTs, definitely check out the BST construction question that we have here on algoexpert.io. That'll cover everything you need to know about BSTs, and it's definitely a sort of prerequisite to this question. Now, without further ado, let's dive into it. This question gives you a BST and a target integer value. And what you want to do is you want to find the closest value to the target value that's contained in the BST. So in front of me, I've got an example. We've got a BST here where every node satisfies the BST property. And then we've got the value 12. Okay, that's our target value. I'll underline it in white. And the answer, the closest value in this BST to 12 is 13, which is located right here, kind of in the middle of the BST. So how do we solve this problem? Well, believe it or not, we're going to be using logic that is very similar to the logic used to implement insertion, searching, and removal in a BST. And so I guess instead of trying to explain it, I will simply implement this algorithm by applying it to this example, and we'll figure out how it works together that way. So let's start from the beginning. We call this function passing in this tree and this target value. The first thing we want to do is we want to initialize a variable that is going to keep track of the closest value in that BST and continually update it. So in other words, at the beginning, we'll have the closest value, I'll write it here at the top. Closest is just going to be equal to, could be anything. I'll just initialize it to infinity because that's going to turn out to be pretty helpful for the code. It's going to simplify something. But, you know, you could initialize the closest value to be the value of the root node. You could initialize it to be, you know, the null value or the none value. Whatever you want, but this variable is going to hold the best candidate for the closest value as we apply the algorithm, okay? And so we start at the root node, and we compare the value of the node that we're at, which is, again, the root node, to our target value, okay? Or yes, before we compare 10 to 12, first we compute the absolute difference between the current value that we're at and our target value. So here we compute the absolute value of 10 minus 12, which is going to be equal to 2. Okay? And why do we do that? Well, we want to see, is this absolute difference between 10, our current value, and 12, our target value, is it smaller than the absolute difference between our closest node and our target node? So we compute the absolute value of our current closest node, which is infinity minus 12, and this is just going to be infinity. And so is infinity smaller than 2? Obviously not. Therefore, that means that the number 10 is closer to 12 than infinity is to 12. That seems obvious, but I guess to put it in different words, the current node that we're at has a value closer to 12 than our current closest node is to 12. And so because of that, we can update this closest here to be 10 now, because 10 is the new closest value to 12. So now we can erase what we computed. And at this point, now we compare the value 10 to the value 12, as in, is 10 equal to 12? Is it less than 10 or less than 12? Is it greater than 12? The reason we do that is because, here at this point, we could do the same thing and compare every single node in the tree or every single value in the tree to our target value. But that wouldn't be optimal because this is a BST. So we can take advantage of the BST property by comparing the two values. And here we notice that 10 is smaller than 12, which means that all the numbers to the right of 10 must be greater than or equal to 10 because we are in a BST. And so that means that every number to the left of 10 must be smaller than 10. And therefore, the distance between every single number to the left of 10 and 12 must be greater than the difference between 10 and 12. So to reiterate that, again in different words, every number to the left of 10 here is farther away from 12 than 10 is, because we know that they're all smaller than 10, and 12 is greater than 10. So we don't have to explore any of these numbers, and we can literally eliminate half the BST that we have to traverse. And so this is where you can kind of notice that we're applying the same logic as we are in the insertion method, the removal method, the searching method of a BST, where we take advantage of this BST property to eliminate half of the tree when we traverse it. So I'm going to remove this line that I drew here, but now we're going to go down this right BST here. So now we are looking at the value 15, okay? So we start by computing the absolute value, or the absolute value of the difference between 15 and our target number, which is 12, and that gives us 3. And then we calculate the absolute value of the difference between our closest value, which was 10, and 12. So if you recall, that was 2, right? 10 minus 12 is equal to 2, or at least the absolute value is equal to 2. And so this time around, 3 is greater than 2. So that means that 15 is farther away from 12 than 10 is from 12. Therefore, we do not update our closest value. And so now we can just erase this, and we can compare our current value, which is 15, to 12. And so we notice that 12 is less than 15. So that means that every number greater than 15 must for sure be farther away from 12 than 15 is from 12. So 22 here can just be eliminated. And once again, we can kind of eliminate half the remaining BST. Or on average, we'll be eliminating half the BST. So now we will explore the left subtree of 15 here. So we go to the node with the value 13, and we compute the absolute value of 13 minus 12. That's going to be equal to 1. Then we compute the absolute value of 10 minus 12, which is the difference between our closest value, the current closest, and our target value. That's going to be 2. And so here we notice that 1 is smaller than 2, so we can now update 10 with 13, because 13 is closer to 12 than 10 is to 12, based on these computations that we just did. And now we, for the last time, compare our current value, which is 13, to 12, and we say, which one is smaller? It so happens that 12 is smaller than 13, so we're going to eliminate the entire right subtree of 13, and we're going to go down the left subtree, so we're going to go down here, and now we're at the end of a branch, right? There are no more nodes. We're just pointing to the none value or the null value. We're at the leaf of our BST. And so at this point, we're done. We can just return the closest value, which is going to be 13. Now, it's important to note that there is one little edge case or one little edge case that we can use to our advantage to make our algorithm a tiny bit more optimal, not really in terms of big O notation, but just more optimal in practice. And that is that if we ever get to a point where the absolute value of the difference between our current value and our target value is 0, we can kind of stop there, right? So, let's say we had been looking for the number, instead of 12, we were looking for the closest value to 15, right? And well, here the answer would be 15, because 15 is actually contained in the tree. And so what we would do is when we get to 15 here, we would say, we would compute the absolute value of 15 minus 15. We would see this is 0. So we would definitely update the closest value to 15. And then we would compare 15 to 15. And we would say, wait a second, these two are equal to each other. Because they're equal to each other, we can just break and return our closest value immediately. Because we know that we've found the exact value in the BST, so we're not going to find a better value. So now let's dive into the space and time complexities. In terms of time, it's going to be pretty straightforward. On average, this algorithm is going to run in O of log of n time. So I'll write it here. Perhaps I'll say average. On average, time is going to be equal to O of log of n, where n is the number of nodes in our tree, in our BST. The reason it's O of log of n is the same reason that most methods on a BST are O of log of n, insertion, removal, searching, because we're eliminating, again, on average, half the tree every time that we explore a node. And so that gives us a time complexity of O of log of n. Now, before I dive into space complexity, let's just say the worst case scenario, so I'll write it here. The worst case scenario is actually going to be O of n. So O of n. And the reason it's O of n is the worst case scenario is when we have a tree that only has one branch. So when we can't really take advantage of the BST property because we never really eliminate part of the tree. So imagine we had the following tree, 10, that points to 15, that points to 22, that points to 30, etc. And we just have one branch, and we're looking for the value, let's say 40. Well, we're going to pretty much go down the entire tree, and we're never going to eliminate half the BST. And so in that case, the time complexity becomes O of n. Now, in terms of space complexity, there are actually two possibilities. If we solve this algorithm recursively, the space complexity is going to be the same as the time complexity. It's going to be, on average, O of log of n, and in the worst, O of n. The reason being is if we implement this algorithm recursively, we're going to be calling the find closest value in BST function multiple times, right? Well, we're going to start by calling it on the value 10, and then we're going to call it on the value 15, and then on the value 13, and so on and so forth. And what happens there is that we're adding frames on the call stack, or we're using up frames on the call stack, and so that means that we're using extra memory. And so on average, we're going to be using O of log of n memory. Now, in other words, we can also say that on average we'll be using O of d memory, where d is the depth of the tree or the height of the tree of its longest branch. But again, in the worst case, when we have a tree that it just consists of one branch, well, that's going to be O of n, because we're going to be calling this recursive function on each and every single node. And so once we get to the very bottom node, we've got roughly n frames on the call stack being used up. That being said, we can solve this algorithm iteratively, and I'll show you how to do so during the code walkthrough. But if we do solve it iteratively, then we get a space complexity of only O of 1, a constant space complexity, both on average and in the worst case, because all we're going to be doing if we solve this iteratively is storing our closest value and storing some kind of variable for the current node that we're exploring. But we won't be using up frames on the call stack. So this is a good example of where iteration or implementing an algorithm iteratively can be perhaps better, at least from a big O point of view, from a memory usage point of view, than implementing it recursively. With that said, let's dive into the code walkthrough to actually see what both of these implementations look like. All right, so we've got our find closest value in BST function defined. It takes in a BST as well as a target value. And the first thing we're going to want to do is write up a sort of helper method, because if you recall correctly, during the conceptual overview, I mentioned that we're going to want to keep track of this closest variable, right? The closest value variable. And especially if we want to implement this algorithm recursively, which is, by the way, the first sort of method that I'm going to be covering here in this code walkthrough, then we want to have this function take in the closest value as a parameter. So what we're going to do is we're going to use a helper method. So here we'll just say returned find closest value in BST helper. And this helper method is going to take in a BST, a target, and a closest value, which, as I mentioned in the conceptual overview, can be initialized to infinity. Depending on your language, here you might want to use, the maximum integer value in your language, or you could even initialize it to be the first value in the tree, the first value of the root node. So now we actually have to write up this helper method. So let's define find closest value in BST helper. This takes in a tree, a target, and a closest value. And since this is a recursive implementation of the algorithm, we want to have a base case, a point at which we stop calling this method. And so the base case is going to be when we reach the bottom of the BST, right? When we reach a leaf. When the current node that we're at is a null node or a none node. And so what we can say here is we can say if tree is none, then we're at a leaf. And so at that point, we return closest. But otherwise, we want to compute the absolute value of the difference between our closest node and our target node. So here we'll say if the absolute value of target minus closest is greater than the absolute value of target minus tree.value, then we update closest to be tree.value. So if our target value is farther away from closest than it is from tree value, then we update closest to be the tree's value. Okay? And now, once we've done that, once we've taken care of the potential update of closest, we want to compare our target value to the current node's value and decide which part of the tree we're going to be exploring. So if the target is less than tree.value, then we want to return the find closest value in BST helper method on the left subtree, and we pass in the same target and closest. So again, if our target value is smaller than the current node's value, then we know we only need to explore the left subtree. So we can call the function recursively on the left subtree. And then otherwise, if the target is greater than the value of the current node, then we can return the recursive function on tree.right, passing in target and closest. And then the last case is if we have a tree that is or a value that is equal to our target value, then we just return closest at this point, because we found the exact value. So there is no other value that could be closer to our target value. And so that's kind of the main gist of the algorithm, right? And so at the top here, we can write the time and space complexities. The time complexity is going to be, on average, O of log of n, where n is the number of nodes in the BST. And as I mentioned in the code conceptual overview, the space complexity is also going to be on average O of log of n because of the frames that we use up on the call stack. Now, if we're in this terrible case where the BST just consists of one huge branch and we're never eliminating any part of the tree, then at that point, both the time complexity and the space complexity are going to be O of n. So O of n time and O of n space. So here I guess I should add space and time. So this is the recursive algorithm. Now let's implement this function iteratively. So I'm going to copy this here, and let's give ourselves a bit of space. And so iteratively, this is going to look kind of similar. We can even keep this top function here, though we don't really have to. Like, we don't really need to use a helper method if we're doing this iteratively. Doesn't really hurt though. And what we want to do here in our helper method is we don't need a base case. So we can get rid of this base case because, this isn't a recursive implementation. So there is no need for a recursive case and a base case. What we do need, however, is a variable that points to the current node that we're exploring. So we can say current node is going to be equal to the tree, right? Whatever tree we pass into this helper function, which is the BST that we were given, is going to be our current node. And then we can say while the current node is not none, so while we are not dealing with a leaf, right? While we're not at the bottom of the tree, let me indent all of this and say, well, here we apply all the logic that we had before. We calculate the the absolute differences, and we update closest if need be. Except this is going to be current node dot value, and this is going to be current node dot value. And then we say if the target is smaller than the current node dot value. Let me replace tree everywhere here with current node. If the target is less than the current node dot value, well, then that means we only want to explore the left subtree, right? So what do? Obviously, we're not going to be calling the function recursively. So we update current node, and we say current node is going to be equal to tree.left. Current node is going to be equal to current node.left. And then similarly here, if target is greater than current node dot value, then we can say current node is going to be equal to current node dot right. And then else, in the case where they're equal, we can just break out of this while loop. And here, whenever we do break out of the while loop, we return closest. And so this is our sort of iterative implementation of the algorithm. You'll notice it's pretty similar. The main difference is that we obviously don't call this helper method recursively, and instead we keep track of our current node that we're exploring here in a variable. But this is just kind of constant space that we're using because we're pretty much only storing two variables, right? Current node and the closest variable. So this is going to run in, let me copy paste the complexities from the top. This is going to run in O of log n time on average, O of n time in the worst case, but O of 1 space in both cases because we simply don't use additional memory. So that's it for this video. I hope it was helpful. I hope it was informative, and I'll see you in the next one.